Okay, guys, so let's start. So last time I explained multiplexer. You should know how as a logic device how multiplexer works. Also, you should know how to design it or implement it using AND gate, as I explained last time. Okay. Um, and also, I told you one of the ways to use multiplexer is to implement functions, and that's what we will do. That's what we do in the lab in this week lab. Also, that's what will be in the quiz. But you need to keep in mind this is not the only use of multiplexer. Actually, multiplexer is used for selection when you want to select data from different sources. Because I'm saying this is the main use of multiplexer. So don't think because I just give you one use to implement functions that multiplexer all the time are bringing them to implement. No. Usually multiplexer are used to select the data from different sources. Okay? So here I explained how can we use AND gates to design to make multiplexer. So I also here is the last part in here is actually how can we use the buffers also to design multiplexer. So now I will introduce a new device with or a new circuit or new gate, whatever you want to call it. Okay, it's called the twisted buffer. I'm gonna tell you what is this, how we use it, and then I will explain how it can be used to design or to make multiplex instead of using AND gates. Okay. So let's start with twisted buffer. Before I go to twisted buffer, I want to define a buffer first. So we have a device, we call it buffer. This is how it looks like, just a triangle this way. Okay, we call it a buffer. Okay. You can see it is very close to inverter, but in inverter we put a bubble here. This one does not have a bubble. Okay, so this device is called a buffer. Okay, so how it works or what is this? What is the device called? Okay, very simple. As you see here, if the input is X, the output is X. So it's not inverter. Okay, if input is X, output is X. The same if the input is 0. Here is 0. It is 1, it is 1. Okay? That's okay. It is not a logic circuit, it doesn't do anything. It's not a logic circuit. We use it for something different. Okay? What is this? I'm going to tell you. So, as I explained to you before, we have something, for example, we call it fan out. Fan out means if you have a gate like this one, so I'm going to cancel the buffer for now, just to understand. Because it looks like this buffer is not doing anything for the logic. The answer is yes. It doesn't do anything for the logic because for the digital, because it looks like 0, 0, 1, 1. Okay? It has, I'm going to use it for something else. So I'm going to explain it now. So as I told you before, we have something, we call it fan out. Fan out means if you check the data sheet of any gate, you will, for example, it's going to tell you fan out is 5. What it means? It means the output of this gate can be connected to only 5, no more than that. So there is a restriction on the output of one gate to how many other gates I can connect to. Okay, there is a restriction. We call it fan out. Okay, why there is a restriction? Why I cannot just connect here 1 million, 1 billion gates? Why not? Okay, the problem is that in electronics, it's not in logic, in electronics. Why? Simply because there is a limit on the amount of current you can take from this gate, and every input here needs a certain amount of current. Okay, I just give you some random number to understand what I'm saying. If the maximum I can take from this one, for example, is 10 milliampere, just an example, and the inputs here, every gate here, it's going to take 2 milliampere, just random numbers. Okay, just to understand the concept of the idea. So let me ask you a question. How many gates I can connect here? No more than 5. Makes sense? Because the maximum here is 10 milliampere. Okay? That's what we call it fan out. Okay? And information like this one you can find in the data sheet of the gates. Okay? So now the question is, what if I want to connect more than 5? If the restriction is 5, but I want to connect more than 5, what should I do? Is that impossible, or there is a way to do it? No, there is a way to do it. The way is the buffer. So actually the buffer, as you see here, in this case, I can connect a buffer here. As you see here, this buffer, it does not do anything for logic. So if the input is 0, it gives you 0. Input is 1, gives you 1. It does not change the digital numbers. But what happens here is it is an electronic circuit. This electronic circuit, this current you take from here, you take a small current, and it can provide much higher current, much higher current. So in this case, this device can help me to connect many gates here. Is that the idea is clear? So number one, from logic, it doesn't do anything. It's output equal to the input. Okay, it's just used for electronics because it is an electronic circuit. When you take electronics, you will take a circuit like this one. You will understand. For example, if you have a transistor or something like that, the input current is a very small current, but you can take from the transistor very, very high current. Yes.
Do you ever have to worry about burning out the other chips when you use the buffer? Because it increases current?
Look, yeah, that's a very good question, because there is something missing here in electronics. So if I tell you, this one takes a small current and gives you 2 high current. Okay, for example, if you take current I, this one is going to give you 100 I. This means it's doing magic. That's how it is. It is doing magic. Because where this current should come from? It has to come from somewhere. You understand what I'm saying? There is nothing that can take 1 I and give you 100 I, because this current has to come from where the 99 I come from. Okay, actually, this one has a bias. This bias similar to what you do with the chips when you connect the VCC and you connect the ground. So is that what you do with the chip? That's what we call a bias. Okay, so this current is coming from this bias, is not coming from the input here. You got what I'm saying? So it's not gonna burn the chips because this current is not coming from here. It's coming from the bias. When you connect this one, there is a bias here. You got what I'm saying? Anyway, so that's what we call a buffer. Now, using this buffer, I can make something we call it three-state buffer. The way we can make it, first, how it looks like. Look at the symbol here. It's a triangle, but instead of having one input and one output, I'm gonna make one more input here. So it has 2 inputs. You see the difference in this one and this one? Okay. So here, this is a buffer. If I make one more input here, okay, I call it three-state buffer. Okay? So a three-state buffer, it is a buffer, but also has a switch, logic switch inside it. Okay, not physical switch. Okay, but it has a switch inside. So that's why it can look like something like that. It's a buffer and also like a switch. Okay? It's not designed this way. It's electronics. Everything is electronics. But this. So how this one works? It's very simple. If the control input in this case is 1, so actually this one is going to act as a buffer. So if it is 1, it's going to act as a buffer. That means output here x and output x equal to x. Okay. However, if the input here is 0, this one becomes open circuit. Okay. So again, if the input here is 1, this one becomes like short circuit. Output equal to the input. If it is 0, it becomes like open circuit. Open circuit, we call it high impedance case. So when you hear the word high impedance, that means it's open circuit. Okay, guys. So again, so this one is still a buffer, but I'm going to use it like a switch. We have a control here. If the control is 0, so this one actually open circuit. Okay. So even if we do anything here, if the voltage is 5 volt or 0 volt, no impact on this one because it's open circuit. But if the input here is 1, so actually we're going to make a short circuit this way. Short circuit means if the 5 volt here, this one becomes 5 volt. 0 volt, this one should be 0 volt. Is that okay, guys? So this is how it works. Okay? I'm gonna explain how can we use this, we call it twisted buffer, how can we use it to create multiplexing. But before I do that, we have, this device has some variations. So for example, sometimes, yeah, this is one of the ways to have this device. There's another way you can just make a bubble here. So what it means, I told you before, every time you see this bubble, that means it's active low. Okay, so this is also some devices like that. So when you have a bubble like this one, that means when the input is 0, now it is active. It's a short circuit. You switch it. Okay, you always will do this way. Okay, but if the input is 1, you actually becomes open circuit. So here these different ways. Okay, maybe this is a very common one, but still we have different variation out of this one. Okay, so actually we can both let's focus first on this one and this one here. Okay, so here this one there is no bubble here in the control input, but this one has bubble here in the control input. So the difference between them is here 0 means open circuit, 1 means short circuit. Okay, here it's the opposite. 1 means open circuit, 0 means short circuit. Is that okay? So this is one of the variation we can do this way. Also, sometimes we can also put a bubble here. So if you put a bubble here, that means you're going to change the logic. So if the input here without a bubble, as you see here, if the input is 0 and this one is connected, so I will get 0. If it is 1, I will get 1. But here, if there is a bubble, so it becomes like inverter. If you have here 0, I'm going to get 1. If it is 1, I'm going to get 0. Okay, so you can invert this. We can put on both, as you see here. Okay, again, although this one is a common one, but still we can do some variation. Also, you need to learn every time you see this bubble. That's what I said multiple times. Every time you see this bubble means it's active low by 0. Okay, so if you see something like that, what it means? If P equal to 0, if P is equal to 0, so actually it becomes like normal inverter. Okay. However, if P is equal to 1, it becomes like open circuit. We don't connect this. Okay. Anyway, so let's see how I can design multiplexer using three-state buffers. Okay. So it's a very simple idea, because actually what we are doing here in multiplexer, if you have 4 inputs and I have 1 output here, so I need to connect based on whatever number you have here in the selection. Either I connect this one to the output, or connect this one to the output, or connect this. Only one of them should be connected. Okay, that means the way I have to use it is only one three-state buffer should be on, and everyone else is off. So if this one is on, so actually here I'm gonna get I note. But I have to make sure as well, if one is connected, the other one should be disconnected. This is the main idea. I give you the details now. Okay. Or if I want to connect I1, I have to make sure if there is a 1 here to connect this one, there must be zeros here to make the other ones open circuit. You got it? Anyway, so let's come to the details. So now I want to make 2-to-1 multiplexer. I have 2 inputs, I have only 1 output. You see here, for every input, I'm going to use 1 three-state buffer. Okay? And now I have to make sure only one of them is connected at a time. Okay? That's why I put this inverter here. Look how it works. If the input is 0, so this one is 0, right? So this one should be off. But this one is 1. Okay? So this one should be on. So I'm going to get A. Multiplexer, I have only one selector. When this selector is actually 0, so the output here is equal to A. Is that okay? Let's look at the other case. The other case, when the input here is 1, so actually this one is connected because it has 1 here, but because of this inverter here, this one is 0. Okay, so this one has to be off. Okay, and in this case, Y should equal B when S equal to 1. Multiplexer. Is that okay? Again, the main idea is I must make sure only one of them in the control here, I have to make sure we have four controls here, okay? Control inputs here, this one, this one, this one, this one. I have to make sure only one of them is one, the other ones are zeros. Is that okay? That's why here, if I want to create 4-to-1 multiplexer, in this case, I'm going to use decoder because that's what decoder is doing. Decoder is going to give me only at the output. One is one, the other ones are zeros. You got what I'm saying? So let's see how this one works. Very simple. If you have the input here is 0, 0. So pin number 1 here is 1, the other ones are 0. This is how decoder works, right? That means this one is off, this one is off, this one off, this one is short circuit. So actually here I'm going to get I0. When the input 0, I will get I0. Makes sense, right? Let's see if it is actually number 1. Okay, so here we have S1, S0. Number 1, it should be this one. Okay, so for example, if you have number 1, so now this one is 1, everyone else is 0. So now this is the one that's short circuit. This is the one that's short circuit, but this one is off. So in this case, I1 here is going to be connected to Y. So Y equal to I1, and so on. Is that okay, guys? So here, all of this can be a multiplexer. So here I can, like a package, if I make a package this way, so whatever inside here, it is a multiplexer. Okay. Also, I have enable here. So this enable for the decoder. So if you disable the decoder, the whole multiplexer is disabled. This is because, as I explained before, if you put here 0 and you disable the decoder, all outputs are zeros. This is how decoder works. All outputs are zeros. That means all of them are open circuit. So nothing. You got what I'm saying? So here again, guys, you can just make this again another way to design the decoder. So yeah, you can make a package this way, and now this will, regardless how what is inside it, that's a decoder similar to the decoder I designed before. Any questions? So the last thing I want to explain here is we have I already explained to guys decoder. We have also encoder, but I didn't explain it yet. Okay, you can tell decoder, encoder. So it should be, it has to do the opposite of encoder, the opposite. Same thing, we have here multiplexer, I explained it. Also, we have demultiplexer. So here we have one device, we call it multiplexer, I have already explained. I have another one, we call it demultiplexer. Okay, again, you can tell from the English name demultiplexer has to do the opposite of multiplexer. How? I'm going to tell you how. Simply, yeah, so here you have multiplexer and demultiplexer. Okay, so in case of a multiplexer, I have 4 inputs, 1 output. I have 4 inputs, 1 output. Okay, and then based on the value of the selector, I'm going to select one of the input, put it here, one of the input here. Okay, multiplexer, sorry, demultiplexer, I'm going to do the opposite. So here I have 1 input, I have 4 outputs, as you see here. And then based on the selector, I'm going to connect this input either here or here or here or here, based on what number you have here in the selector. You can understand? So we have another device, we call it demultiplexer. You can see the difference between multiplexer and demultiplexer. Okay. By the way, in communication, multiplexer and demultiplexer are very widely used. In communication, multiplexer and demultiplexer are very widely used. Okay, I'm going to tell you why. If you have here a cable, if I want to connect, for example, here, everyone here is a user. I want to connect, for example, using this configuration, because if you look here, this is the analogy switch. So it looks like that, okay, like a switch is this way. So I can connect here input 1 with input 1 here, or input 1 to input 4. But I can connect here 4 to 4 or 4 to 3. So I can connect any input here to any output here, okay? By using the selectors. So it's very widely used in communication if you want to transfer data from one place to another, okay? So now, how can you design this demultiplexer? Any question about what is demultiplexer? Just do the opposite of multiplexer. We have only one input. We have multiple. It's still a switch. Multiplexer or demultiplexer. It's still a switch. You connect. Okay. But this one is gonna connect one input to multiple output, depending on what number you have here in the selector. Okay. So here I want to tell you here is one way to implement this demultiplexer. One way to implement the demultiplexer is actually using a decoder. I'm going to tell you how. So I don't need to design a new logic circuit for demultiplexer. A decoder, I can twist a little bit the way I will use a decoder to make it demultiplexer. How? I'm going to tell you how. Number one, here, you know, in decoder we have input here. So this input this will be the selectors, and I will pick the enable, and this enable is going to be the input, and this is the output. So if you have a decoder, and I can use the enable as input, because if I come here, see what is demultiplexer? We have input, we have output, we have selector. So I can use the input here in decoder as a selector. I'm going to use the enable here as input, and then we have output here. How it works is very simple idea. Look here. First of all, when the enable is 1, okay? So when the data is 1, for example, and here, for example, I have number 0, 0. So actually this one is 1 here. Okay? So if the data is 1, or if you have here, for example, number 3, so this one is the 1. You got what I'm saying? So if the input, just let me finish. If the enable is 1, and the input here is 1, so actually the 1 will come here. So based on, so this is like a selector. When the input is 1, I can select which one should receive 1 here, okay? But if the input is 0, for example here, so for example, if I work in D2, this one becomes 0, okay? So that's why I can use, if for example, if I want to use D3, as just an example, I want to use D3, here, so here I'm gonna put number 2. Number 2 is actually 1, 0, number 2. Now, based on what is the input, this one should receive 0 or 1. If the input here is 1, okay, the decoder is enabled, and because it's enabled, and because I selected T2, it is gonna receive 1 here. Similar to the input here. But if I make it 0, so the decoder is disabled, and then I will receive 0 here, similar to the input. So I selected one output here based on this value here, and based on the input, I connected to the enable this way. So the output I selected is gonna receive the same value like the input. Okay. Again, maybe this is a simple way, but maybe there are other ways to do it. But we're not gonna investigate this further. Just very simple idea to just introduce the concept of demultiplexer. Yes, you have a question?
Can you go back a slide?
Yeah.
So on that demonstration on the bottom from
Yes.
the multiplex to.
This is analogy. It's not real implementation. Analogy. Okay. So it's like this one look works like a switch, right? You connect one or output here to one of the inputs. Okay. This one also works as a switch, but connect one input to multiple outputs. That's why you can like a switch in this one.
Yeah, but the selectors, would those selectors on both chips have to always be the same, or can you change it?
Yeah, for sure. It depends on the application, but for sure it depends on what you want to do. But you have, for example, if I want to connect, if I want to send data from line 1 to line 4, so here I have to put number 1 here and I have to put number 4 here. You got what I'm saying? It doesn't need to be exactly the same number all the time, because this is the beauty of it. The beauty of it. This input I want 1 here, I can connect it to 1 or 2 or 3 or 4. You got what I'm saying? But if you want to make it the same number, so all the time this one is connected to this one all the time. Is that clear? So here, yes, you can, for example, if I select number 1 here you can, based on the selector you have here, you can select anyone so that I can connect number 1 to number 1, or I can connect 1 to 2, or 2 to 3, or 4. Okay. Any questions? Anyway, so let me tell you now my plan, how we will move forward. So here in this chapter, I explain what's combinational circuit. Here, this one is done. This one is done. This one is mostly done, but there is a small part at the end. I will explain it. I will leave this one for now. Okay, I will leave this one for now. Here, I didn't explain decoder, but I explained decoder. This one is completely done. So what I will do right now is I need to move to chapter 5, but because I need to finish some part in chapter 5 that I need to learn, And then after I'm done chapter 5, I will come back to chapter 4. And don't worry, the flow of the course it should be okay. So there is no problem about it. But I need to teach the topics I need for labs first. Uh, I want you to pay much attention to chapter 5. I hate to use the word difficult. I don't think anything is difficult, but compared to the other stuff we have in this course, yeah, chapter 5, you need to pay more attention to it. Okay. So here in this chapter 5, I'm explaining sequential circuits. So if you remember, I told you before, as I told you before, guys, in logic circuits, we have two types of logic circuits. One type here is combinational circuits, and that's what we have done so far. Every circuit we had so far in this course every circuit is combination. Everything we did is combination. Okay. So, and we have also something else, we call it sequential circuits. So that's what I will start teaching in chapter 5. Okay. What is the main difference between them, as you will see? In combination circuit, and that's what we have done, okay? Always for the same input, so for example, every time the input is 1, 1, 1, I will get 1, for example. All the time. There is no way to give this input. One time I get 1, one time I get 0. It never happened. You know what I'm saying? This is combination circuit. So if every time you put input, you get only one output, or here in other words, the output depends only on the input. This is a combination circuit, and that's what we have done so far. If you think, or if you go back for everything we did so far from the beginning of this course until now, you will never find a case I input some value and one time I get 1, one time I get 0. It never happened. Okay, and this is the main difference between sequential and combination. In sequential circuit, the output does not only depend on the input, okay, but also depend on the state, okay, in the current state. Okay, that means it may be for the same input. If the state is different, I will get different output. Okay, but for sure, for the same input, for the same state, I will get the same output. So again, the output here depends in two things. One is called input, similar to this one, and also here what we call a state. So that means, for example, if the system, as I'm going to explain, we have two states. I have state 0 and state 1. For example, if I'm in state 0 and the input was 1, maybe the output is 2. The output actually, for example, 0. Okay. But for example, if the input is 0, okay, here the output, for example, is 1. Okay. So here, that's what I want to show you. So here, if I'm in state 0, so it depends on the state. But for example, if I come here, if the input here is 0, I'm gonna get 1. Okay, so that means if you see here when the input was 1, I got 0. Here when the input, sorry, this is the input. Okay, I want to say the same thing. Here the input is 1, I got 1. Okay, so in this case, when the input is 1, I got 0. But here the input is 1, I got 1. How is that? Simply because this was in a different state. Okay. So again, here the output, for sure you will understand better as I explain more. But for now, you should understand the output here does not only depend on the input, but also the state. Okay. For sure, for the same state, same input, you will get the same output. That's for sure, all the time, for sure. You got what I'm saying? But for the same input, for example, if the input here is 1, maybe I'm going to get different output in different states, maybe. Okay. So anyway, so you understand what I mean by state, how can you make states? Okay, because actually here in sequential circuit, what happens here, we move from one state to another, as you will see. Okay. So the first thing I need to teach is how you will implement this idea of states. So how you implement it? Very simple. Okay? Look here. I'm gonna use a storage unit. Okay. we call it flip-flop. It's a device I'm gonna explain right now. So we have something, we call it flip-flop. Flip-flop is actually a logic circuit. This logic, it's a storage unit that can store 1 bit. So you have a circuit. I'm gonna teach how I design this circuit, but this circuit can design 1 bit. This bit can be 0 or 1. A storage unit that can store only 1 bit. We call it a flip-flop. Is that okay? I will give you more details. So actually what happens is that if your system has 2 states, I need only 1 flip-flop. Why? Because, so here, this is how I'm gonna store the state. Simply because if the flip-flop is storing 0, so I'm in state 0, okay? But if the flip-flop is storing 1, so I'm in state 1. Okay? Okay, now, if the system has 4 states, so for example, you have state 0, you have here state 0, you state 1, state 2, state 3. And you are actually moving from one state to another as I'm going to explain in details. In case you have 4 states, how many flip-flops do you need to store the states? Okay, actually I need 2 flip-flops. So this is the circuit should have 2 flip-flops. Because in case of 2 flip-flops, if you are storing, if again, flip-flop, as I'm going to explain in details right today or next time as well, it's a logic circuit that is a storage unit. It can store 1 bit. How you will make it, I will explain in very detail how can we make it. But for now, just we have a storage unit can store 1 bit. That's it. Okay? And you can change the state. So if it's storing 0, I can change it to 1, but it's still storing only 1 bit. Okay. So now I need 2 flip-flops. So if the 2 flip-flops are storing 0, 0, so actually I'm in state 0. If it's storing number 1, so I'm in state 1. If they're storing number 2, so I'm in state 2. If they're storing number 3, I'm in state 3. And so on. You got what I'm saying? So anyway, you will understand better as I teach you more, but now for now, we should understand sequential circuit is different from combination circuit. In sequential circuit, I have to use flip-flop to make states. Okay? And the system should change state from time to time, as I'm going to explain. You change the states. Okay? So maybe the system is here now. Okay, and next time I can come here or I can come here. Okay, next time based on the input. Okay, maybe I'm gonna move from here to here or to here to here in next time. Okay. So let me read here what we are doing here. Yeah. So here all circuit we design for so far are combinational. So here actually, so the state states are stored in the is actually stored in the in the bits by flip-flops. So flip-flop can tell you what is the current state. Okay? So anyway, so as you will see, we have a memory element. So that's what I told you. This the memory element here. That's what I'm explaining. All sequential circuits should have memory element, and this memory element actually flip-flop, as I told you. Okay, and actually we have something like a feedback unit. Why? Because actually what we have here is the state. The value of 0 or 1, what is stored here is the state, okay? Because the new output should depend on input and state as well. That's why I need feedback. So I'm gonna take this state, I'm gonna take it as a part of the input here, okay? So actually what, as we see here, most of the time what we need, or always we need memory elements like flip-flop, okay? Also, I'm going to use some combinational circuit to connect it to flip-flops. But again, this is the whole circuit is sequential. It's sequential. But still, I'm going to use some combination inside it. But everything here is sequential circuit. Okay? So if it's sequential circuit, it can be XOR, whatever it is. Okay? But this circuit has inputs. Also, it has the speeds. And based on that, I'm going to decide what is the output. So the output here depends on both on the input and state. Okay, anyway. So don't worry if you don't have 100% understand everything I explained. I just the purpose of what I'm doing right now, just to give you big picture, just a big picture, because for sure I will give you everything in very details. I'm gonna show you how can we design the flip-flop first. This is the first part I will do right now. I'm gonna start teaching how these memory elements. How can we design these memory elements? Okay, and then after that, I will explain how can we use them to create sequential circuits. Okay, but for now, I'm just explaining the difference between sequential circuits and a very high level description, the difference between sequential circuits and combinational circuit. But I will give you everything in details. Okay? So let's start with the first one here, memory elements. That's what I'm going to start teaching, memory elements. So in memory elements here, it's memory, okay? It can only store 1 bit. Okay? But it's different. Don't think about your hard disk or memory stick or something like that. No, it is a logic circuit. And if you have a flip-flop, and this flip-flop is storing 0, okay? So as long as the power is connected, it is 0. Once you disconnect the power, it's gonna lose the information. You understand what I'm saying? So as long as you connect the power, it's gonna store 0. Unless you change it, because there is, as I will explain, there is a way to change this number, okay? So usually you have two input, one for reset, one for set. One for set, one for reset, okay? So if I wanna store 1, so I have to activate the set to store 1. If I want to store 0, so I have to activate the reset to store 0. Okay, so just 1 unit. This unit can store 0 and 1. You can change it. It's not only one time, you can change it. Okay? So anyway, so here, in the second part here, I will start teaching storage elements. And for storage elements, actually we have two things. One is called one element we call it latches, and the second one we call it flip-flop. You will see what is the difference between them, but I need to start teaching latches because actually we're going to use latches here inside the flip-flop. It's like this, right? But this one can be, you will understand what is the difference between them, but both of them are storage elements. So every latch can store 1 bit. Every flip-flop can store 1 bit, and you can change it. So it's completely okay. But there is a difference between them. You will understand. Okay? Any questions? Again, make it easy. So what I'm saying is, for sequential circuit, we need storage units to store the state, because the output does not only depend on the input, but also depends on the current state. And the circuit should change states. I mean, state 0, state 1, state 2, state 3, and so on. And these states are stored by storage unit, okay? And this storage unit can be latch or can be flip-flop, but most of the time we use flip-flop. But anyways, flip-flop is actually part of latch, okay? So everything I will explain right now, guys, we have different types of latches. We have different types of flip-flop. Everything I'm going to teach right now is actually doing one thing. We have a circuit, whatever the circuit is, whatever you call it latch or flip-flop, I don't care. This circuit is storing 1 bit. This bit can be 0 and 1. Okay? And also, I can change it. So I have reset and set to change the value or storing. Okay? So I'm going to teach right now how can we use logic circuits to make this latch storage unit, store 1 bit. Okay? So I'm going to start with the first one here. So number 1, I'm going to teach what we call SR latch. This is the first type of latch here. We call it S here. S here is standard for set. R here is standard for reset. Because I told you here we need 1 input for reset, 1 input for set. To set the value or storing here, to reset the value or storing here. So here we have SR latch. I'm going to explain it. I'm going to implement it in 2 different ways. I can implement using NOR gate, as you see here. Also, I was just going to give you the big picture before I move forward. Also here, I can implement SR latch using NAND gate. So one time I'm going to make it using NOR gate, and then after that I will do it using NAND gate. After that, I'm going to add enable to it, SR latch with enable. Then after that, I'm going to make what we call G-latch. So here, I explained SR latch. After that, I will explain G-latch. G-latch. Okay. I think that's it. Yeah, that's it. Then after that, I will, because we use G-latch here. So here, G-latch. Yeah, for sure, you can use G-latch alone. Okay, but I'm going to tell you why usually, but not usually, it depends on, I'm going to tell you why. So this G-latch, I'm going to use it here inside to create flip-flops. But also I will tell you the difference between them. But sometimes you can use the G-latch alone. Okay? But for sure I will give you this. So all what I'm going to explain now is SR latch using NOR and NAND and also DLATCH. So let's start here. But everything everything I'm gonna explain is actually, as I told you, is a storage unit to store 1 bit. So let's see how SR-latch is working. So if you see here, this circuit here, we call it SR-latch. Let's see how it works. Is this is a storage unit? So this is here as a unit this way, as a unit here. Is this a storage unit or is it? It is a storage unit. Okay. So what is the stored value? The stored value here. So you have a block here. You have a block. This block has what we call Q, and it has Q prime. Also, it has two input R and S. Okay. So what is Q and what is Q prime? This is the stored value. So the stored value is Q. So I give you the stored value and the complement of the stored value as well. You understand? So if this device is storing 0, you should see here 0 and you should see 1 here. If this flip-flop is storing 1, sorry, if this latch is storing 1, so you have to see 1 here and you have to 0 here. You got what I'm saying? So the stored value, I give it to you in Q. Q is the stored value. Q prime is the inverter as well. Okay, so I give you 2 outputs. One for the stored value, one for the inversion of the stored value. And then it's up to you which one you want to use. You might not use one of them. You understand what I'm saying? It doesn't mean we usually like to do that. Like I think in the older multiplexer last time when I explained, you are gonna get 2 outputs. One with inversion, with one without inversion. It doesn't mean I'm gonna use both of them. It doesn't mean that. Sometimes you use only one output, but you have both of them. You have the stored value and you have the complement, and it's up to you. What it depends on your design. What you need in your circuit. Do you want to use the stored value? It doesn't mean I have to use both of them all the time. No, I mean only use one of them. Okay, guys. Anyway, so here I'm gonna explain how this one works. But for now you should understand we have what we call SR-latch. This is SR-latch. It has 2 outputs. It's actually one output, but one output is a stored value and the complement of the stored value. Okay, and we have 2 inputs here. The purpose of these 2 inputs to control the stored value or to change the stored value. This is the conclusion before I give you more details. Look here, guys. If the 2 inputs are 0, 0, that means there is no change. So here, if you input 0, 0, that means there is no change. No change means if you are storing 0, it's going to continue storing 0, no change. I don't want to change the stored value when it is 0, 0. Okay? But if I put here 0 at S, if S is 0 and R is 1, so actually I'm gonna make a reset. So this one is active high. So whatever 1 is gonna activate it. So if I want to reset, if I want to store 0 by this device, so here R has to be 1, S has to be 0. Okay? If I want to set, if I want to store 1 in this element, so I have to put here 1 and 0 here. Okay? And forget the last case, I will talk about it right now. Okay, so conclusion, this is like a big picture before I give you the details. I have a latch, we call it SR-latch. This can be stored to store only 1 bit. This is the stored bit here, we call it Q, okay? And you have the inversion of the stored value. That's why these 2 outputs should always inversion to each other. They must be. If this is 0, this should be 1. If this 1 should be 0. Must. Okay? Anyway, also, the way it works is here, we have 2 inputs. This one is active high. So if this one is 1 and this is 0, so I'm going to make a reset. Reset means I'm going to store 0 in this end. This end is storing 0. But if I make it 0 and I make it 1, so actually I'm going to set. So that means this one is storing 1. If I input 0, 0, that means there is no change. If it's storing 1, it's going to continue 1, 0, no change. Okay? So now I will give you more details. So in order, if I want to make the circuit here, the way we do it, I can do it here. This one, I'm going to do it using 2 NOR gates, as you see here. So this is a NOR gate here. I connect R here, the reset here, R, the reset. I connect the set input here, and the output of this one is connected here, the output of this one is connected here. And this is Q, and this is Q prime. Please, guys, you understand what I mean? What I mean by Q, this is a stored value, because this is a storage element. It can store 1 bit. The stored value is Q. I give you the stored value and the inversion of the stored value in order to control what value you want to store. Okay, I want to store 0 or 1. I have two inputs, one for the set, one for set. Okay. But okay, tell me how this circuit here will do what you told us here. Okay, I'm gonna tell you, but before I tell you, I just wanna remind you of how NOR gate works. The way NOR gates work is if one input is 1, regardless of what you have here, the output is 0. Because NOR is actually OR and then inverter after OR. And OR, if one input is 1, is that okay? So regardless of what you have here, the output here is 1, inverter make it 0. Make sense? So again, this is how NOR works. If one input is 1, regardless of what you have here, regardless, output right away is 0. However, if one input is 0, okay, here this one is X, so I'm gonna get X prime. That means if this one is 0, I'm gonna get 1. 1, I'm gonna get 0. Okay. Again, this is because it's very simple, guys. This is because we have OR. After all, we have inverter. If you go back in the first lectures, in this course, I told you 0x should equal to X. This is for the OR. Inverter make it X prime. Okay. So again, I don't want to spend much time on this one. So here you can see this is how NOR works. Based on this one, I will show you how this circuit here is gonna do what I promised here. Okay. So let's see how it works. Number 1, I told you if I put here 1 0. 1 0, what should do 1 0 here? It has to do reset because this one is active high. Whatever is 1 is gonna be active. We have one input here. Look here, guys. We have R and we have S. Whatever 1 is gonna be active. Okay. Because I'm going to show right now, sometimes, and that's what I'm going to explain here in when I use NOR, or sorry, when I use NAND instead of NOR, this one actually active low. Active low means if I want to do set, whatever is 0 is going to make a set. If I want to do reset, because I have two inputs, it's and R, but whatever 0 is going to be active. It's the opposite of what I'm explaining. Okay? But this one is active high. So actually, if this one is a 1 and this one is 0, so it's gonna be reset. If the set is 1, so it's gonna make a set. Okay. But let's see how this happens. Look here, guys, very simple. If you go between 1 and 0, I told you based on what I explained here. If this one is 1, so what is the output here? 0. Regardless of what you have here, regardless, I have 0. Okay. And then 0 will come here. 0 0 will give you 1. So all the time, 1 0 is gonna give you 0 here. And always this one is a complement of this one. And this is a stored value. So that's why when you omit 1 0, I'm gonna store 0. This is the stored value. And this is the complement of the stored value. Make sense? Very interesting. Let's see something else. Also, I promised if we make this from this table here, if I make this 1 1 and I make this one 0, I have to make set. Let's see how. This one is 1, so this one is 0, regardless of whatever I have here. So if you have here 0 or 1, it doesn't matter. If you have 0 or 1, it doesn't matter. Once this one is 1, so I have here 0. And this 0 is gonna come a feedback here. 0 and 0, so this one should be 1. And this is a stored value. So here, yes, if there is a 1 here, 0 here, I'm gonna store 1. Make sense? Okay. So now I did this one is correct. This one is correct. Now let's go to this one. No change. Okay. No change means if I'm storing 1, I will get 1. If storing 0, I will get 0. No change. Okay. So let's see. If that's third case, if you just put 0 0. So that means if I'm not gonna do reset because it's 0, it's not 1, I'm not gonna do set. No change. No set, no reset, no change. Okay. Look how it works. Based on what I did here. So whatever value here, I'm gonna call it X. Okay, for sure, this one should be. So whatever value here, I'm gonna call it X prime, and we have here X. So whatever value here is gonna come here, and it's gonna be actually inverted. So if you have here X prime, I'm gonna get X here. So that's why I'm telling you no change. Same thing here. If you have X here, and then look at this one here. Okay, so I'm gonna get X prime again. So let me give you some numbers. You don't like symbols. These are numbers. Okay, very simple. If 1 and 0, for example, if I'm storing 0, so this one is gonna come here. And based on what I'm explaining here, if one input is 0, and so here I'm gonna get the opposite of this one, so it's still 0. And this 0 is gonna come here, 0, 0 give you 1 again. So 0, 0, if the two input 0, 0, will not change. Anyway, okay, guys. The last case that I didn't talk about it, what about if you input 1 and 1? Why you call here forbidden case? Simply because if I put here 1 and 1, look at this one here, what I put here. So actually I'm gonna get 0, 0. This is a forbidden case. Why forbidden case? Because always the Q prime has to be the complement of Q. So this is how this device should work. I have two output. One is Q, this is the stored value, this is the complement of the stored value. So always there should be a complement. If they are equal, it's false. It's false. It shouldn't be this way. That's why I'm saying this case is forbidden. Because in this case, if you put 1, 1, I will get 0, 0. And it's not gonna work as I need. That's why we should not use this case. So if you want to use, or usually if you want to use the SR flip-flop using NOR, okay, we are gonna only be limited to these 3. I'm not gonna use this case. You should not use this case. Okay, guys, any questions? I'm gonna repeat it. Very simple, very simple. So here, in case of SR flip-flop, latch, I'm sorry, I used that because actually most of the time we use flip-flop, honestly. That's why this is a latch, not flip-flop. You will see there's a small difference between latch and flip-flop. You will see, okay, but it's a correct way. It has to be latch, not flip-flop. Okay, so for this latch, we have here output Q, and we have Q prime, and you have here R and S. And it's very simple. Look here, guys. If this one is active hard, so if this one is 1 and this one is 0, so actually I'm gonna store 0. Well, I'm storing 0. I'm doing reset. But if the S is 1 and R is 0, so actually here I'm storing I'm doing set. So that's why I'm storing 1. Okay, 0, 0 no change. That's it. 3 cases. 0, 0 no change. Okay. After that, whatever 1 is gonna be activated. If S is 1, you set. If reset is 1, you reset. Okay? And for sure, 1, 1 is a forbidden case, as I told you. Okay? So again, this on latch I can draw. It can take different symbols as you see here. For example, here I can say this is. If you look at this symbol, this is SR, and then I have a bubble here. This is a bubble. Just to tell you, this is U and this is U inverted. Okay? Sometimes we do this way, RS, and then I'll tell you this U prime. So again, there are different ways to do it. Okay, this is just here. I want to show you how it works. So if you see here, guys, 0, 0, if it is 0, 0, okay, 0, 0, what I told you, 0, 0 means no change, right? No change. This is a case of no change. That means if it is storing 0, it's gonna continue 0. If it is storing 1, it's gonna continue 1. Because it's no change. But look at this case here. When R is 1 and X is 0, here you are doing reset. That means if the input is 0, the output also 0, because it's going to be reset. No matter what, it's reset. If it is 1, so now it becomes 0. You are doing reset. Regardless what value it is storing. If storing 0 or 1, it doesn't matter. I'm doing reset. The output, regardless what value it is storing, I'm going to get 0 because I am doing reset. In case of set, here, the 1 is here under S, the 0 here is under R. In this case, no matter, regardless what value you are storing, 0 or 1, I'm doing set. The output is 1. You are want to store 1. Make sense, guys? The last case for sure, this is a forbidden case, we should not use it. When you have 1, 1, so here in this case, 1, 1, I'm gonna get 0, 0, which is the forbidden case for Q and Q. Okay. Any questions? Okay. Usually in latches and flip-flop, and to understand how they work, usually we have a timing diagram like this one. And in the coming quiz, not today's quiz, but the next quiz, it will be something like that. I will give you the R, I will give you some input, and then I will ask you to draw Q and Q prime. But I will do that for flip-flop, but it's going to be the same thing like this. Okay. So usually we use timing diagram to better understand how it works. Okay, so let's see here. Forget what we have here. I will draw it. So I will give you input. This is the input here. This is X and R. Look at here. This time is plot here, guys. In this time plot, R1 is of 0. So what should happen to Q? Okay, so Q here, assuming that start from 1, but here I'm doing reset because R1 is 0. So that's why this one should be reset. Okay, and Q prime is going to be the opposite. Q prime Q prime is complement of Q. It makes sense? So again, I'm very clear. In the coming quiz, I will give you input, then I will ask you to draw this one part here. Okay? It will be something similar to this one, but it's going to be for flip-flop. But usually when we teach lectures for flip-flop, using such a diagram, make it easy to understand. Okay? Let's start what happened next. What happened next here in this time slot, we have 0, 0. What 0, 0 means? No change. That means if you are 0, here I'm 0, you have to continue 0. If you are 1, you have to continue 1. But here, in this specific case, I'm 0, so I have to continue 0. Make sense? Let's look at the next one. We have 1 and 0. This one is active high. So S is 1, R is 0. That actually, I'm doing a set. That's why in this time slot, it has to be set. For sure, this one is going to be 0. Okay? Now, this one is 0, and this one here, R is 1. That means I'm doing reset. So this one has to come here, reset. So at any time when you change R or S, so based on what value you have here, this is the stored value is here, and this is the complement of the stored value. Okay. Here after that we have here 1 and 0. This one is active high. 1 here at S, so here S has to be 1. Makes sense? It's easy, right? So actually here, this is the table here I have. I implement it here in a diagram. So, any questions? One more thing I want to bring it to your attention, because if you read the textbook or if you read also, I'm not sure if Zybox is doing it this way or not. So here, actually, although just because I want you to understand how flip-flop works, how latches works, I'm assuming all signals here are ideas. Because if I assume it is ideal this way, this will make it easy for you to understand how flip-flop works. I don't think in the textbooks they are not doing this way, and I didn't like that because this makes it harder to understand the topic. Okay, so what do you mean it's ideal? That means just here it's easy here to understand. Yeah, 0, 0, this should be 0, and so on. It's easy, right? But actually, in reality, these signals are not like that, and that's what you should already learn from lab. Usually there is some rise time. Usually there is a fall time, rise and fall. So it shouldn't be this way. There should be some rise time and fall time. Yes, I just ignored it because I want you this better to understand. If I do this way, it's easier to understand how latches and flip-flop works. Not only that, so here same thing here. There should be some rise time here. Not only that, also there is a delay. Because I'm saying, so what I'm saying here, when this just once this one becomes 1 and this one is 0, right away this one will be 1. What you limit in the labs, that's not true. There is a delay. Okay, so in reality, it has to be this way. This one should be increased a little bit. It takes some time. Also, this one it should not start from here. It should maybe start from here. You understand what I'm saying? It should start from because it's the impact of the delay. So in all this chapter and next chapter, I'm ignoring the impact of rise time, fall time, and the delay, just because I want you to focus on ones and zeros. It's easier. It's like this. I hate when I found it the books this way. I didn't like it. Okay, that's what I'm saying here. What I'm saying here, always we have rise time and fall time, and also we have a delay. Don't think when this one go high and this one is 0, it's gonna be high immediately. No, there is some delay. Okay? Yes, we understand that, but it's easier to, when I teach flip-flops, it's easier for any logic circuit to assume it is ideal. Okay? Any questions? Okay. The next thing I want to teach you guys, nothing is new. It's exactly the same thing as I taught here. It's exactly the same thing. The difference is that instead of using node, I'm going to use named. So here, instead of using node, I'm going to use named. You will see I will get the same, everything is the same. Everything is the same. However, this one, it will become active low. So that means if you want to do a reset, okay, or when this one is 0, so actually you are doing a set instead of reset, okay? Same thing here, is when this 0, so here I'm doing a reset. This one becomes active low. Also, the forbidden case is actually 0, 0 is 0. Okay, this is the forbidden case, 0, 0. The no change case is actually 1, 1, 1, no change. You got what I'm saying? So it's gonna be, if just I replace node by red, I will do, I'm gonna get, see, everything is the same. But now this one becomes active low. Whatever 0, if S is 0, so it's gonna make a set. What we have here, if S is 1, you make a set. You got what I'm saying? So that's why almost everything is the same, but it's active low. So that's why here, so it's the same thing here, guys, but I use the NAND instead of loop. Again, I want you to remind you of how NAND works. Okay? This is how NAND works. If one input is 0, so regardless of what you have here, I'm gonna get 1. Okay? If one input is 1 and you have X, so here you will get X prime. Okay? Again, because NAND is actually AND followed by inverter. Okay? And in case of AND, if one input is 0, I'm gonna get 0. Regardless of the other input. And then because of the inverter, I will get 1. Okay? So I will show you now how using this tool, how this work is this one. Okay? Let's start, for example, with set 0, 1. So here I put 0 and 1. Okay, so this one active loop. So whatever 0 is gonna be active. So here 0 and 1. Okay, so based on what I'm teaching here, if one input is 0, this one should become 1. Okay, and 1, 1, I will get 0. So now if S is 0, R is 1, so here I'm gonna store 1. Set. Okay. Same thing if you look at the other case. If I put here 0 here and 1 here. So now this one has to do a reset. Let's see. Because if this one is 0, regardless of what you have here, this one becomes 1. 1, 1, you get 0. So now you are doing a reset. Make sense? Now let's look if I input 1, 1. Yeah, look at this case here. 1, whatever you get, you complement it. So what happens here, 1, and then I get Q prime. So I'm gonna complement here. That's why there is no change. For example, if it is 0 and 1. Okay, so here this 1 and 1 give you 0 again, no change. If I get here 0, okay, I'm gonna complement the 0, get 1 again, no change. What is the forbidden case here? The forbidden case here, it is actually 0, 0, not 1, 1 like that one, 0, 0. Because 0, 0 will give you 1, 1, which is a forbidden. Why it is forbidden? Because this output should always be complement. This output should be complement to each other. It doesn't make sense to have 1, 1 or 0, 0. Okay? Any questions? Everything here is almost the same. So for example, if you see here you have 1, 1. I told you 1, 1 here no change. So if you have 0, it becomes 0, 1 becomes 1. Okay. Here you have 1, 0. This one is active loop. So whatever 0 should be active. So this one is reset. Here, this one is actually set. 0, 0 is the forbidden case. Okay. Same thing for this diagram here. Okay. If you look at this diagram here, guys, if you look here, if this one is active low, so whatever 0, so here R is 0. So that's why here the output is 0. 1, 1 is no change. That's why, because this is 0, it's going to continue 0. For sure, Q prime always the opposite. It's a complement of Q. Now you have here 0 and 1. This one active low, so actually S is 0. So this should be high during this time. 1, 1 no change. So it's going to be continued high. Okay, guys. Again, that's enough for today. Next time I will continue teaching this part, but again.